Welcome to the Astrophysics Podcast. You might not know this, but most stars are actually in binary star systems. That is to say, two stars orbiting one another about a common center of mass. In science fiction, the most well-known example of this is Luke Skywalker's home planet of Tatooine, which had two suns that were in a binary system. Since most stars are in binaries, maybe having only one sun is the exception, whereas two suns might be more common. Of course, that depends on how common it is for a planet to orbit a binary system. As you might guess, binary star systems are more complicated than single stars, meaning they are much more difficult to model and compute their evolution. However, understanding binary stars is crucial to almost every other field in astrophysics. For example, it tells us how these stars can eventually explode as supernovae, or transform into more compact objects like neutron stars and black holes. Our guest today is a leading expert on how binary star systems evolve. Her name is Dr. Katelyn Breivik, and she is a professor of physics at Carnegie Mellon University. Dr. Breivik is one of the lead developers of a computer code that can evolve simulated binary systems from birth until death in order to learn more about the way stars in our galaxy behave during their lives and what they turn into after they die. I'm Paul Duffel, and this is the Astrophysics Podcast. So that's basically why, rather than having you go on a long tangent or monologue about your standard monologue you give to public.
Right.
I try to cut you off as soon as you jump into that. I go, no, we're not doing that.
Okay. I won't take it personally.
Okay, good.
I'll leave this meeting and tweet. Just had the rudest meeting.
On the Astrophysics Podcast. Don't listen to it. It's terrible. He's so rude. Welcome to the Astrophysics Podcast. I'm Paul Duffel, and my guest today is Dr. Katelyn Breivik, professor of physics at Carnegie Mellon. Dr. Breivik, thank you for joining me on my little podcast.
Thanks for having me.
So I guess I want to start by talking about you personally and how you grew up to be a scientist before we actually talk about the scientist. So where did you grow up?
I grew up on the east benches of Salt Lake City in Utah.
Okay.
Yeah.
So you were not in Salt Lake City. You were like a small town outside of it?
No, Salt Lake is a pretty small geographical, it's like a geographical bowl with mountains on either side. So I was like 10 miles outside of the city, but we could see it. It was like very suburb.
You were actually, okay.
Yeah,
yes, yeah. So what was that like growing up there?
It was kind of weird. It's weird. People who know Utah know that Utah has had an explosive growth in the past maybe 10 years. So when I was there, we lived a very working class, more rural life than you might think when I say suburbs. So for example, we did mostly like hunting and fishing activities as kids.
I see.
Which was not something that you might think.
Urban activities.
No, it wasn't very urban. Yeah.
But okay.
Yeah.
And so then, do you have any memory of like the first time you knew you were interested in science or anything?
My family's not like really a big science family. My mom's dad was a doctor, and all of her siblings are all either accountants or doctors, and then my dad's side is like super working class.
Okay.
And so I didn't really have a lot of science like influencers in my life as a young kid, but I spent a lot of time looking up at the sky because for whatever reason my parents thought that was important for us as kids. So
to just stargaze and...
Yeah, literally. So we spent a lot of time, we built a cabin on a lake like 3 hours outside of Salt Lake. The lake is called Bear Lake, and it has bonkers good dark skies.
Okay.
And so like we would every weekend for the first 17 years of my life, basically we were building this cabin up under dark skies. I had like no social life. So we'd drive up every Friday, and my dad, like after work and whatever, we'd all be like ready to be done. We'd unload our car, and then my dad would be like, no one can go inside until everyone sees the same shooting star. which sounds crazy, like weird dad thing.
It does sound like a weird dad.
But it took like 5 minutes because there were so many shooting stars. But so I grew up literally every weekend, like that was our like family thing, was to look at shooting stars. It's a little bit hokey. But yeah.
So you had so you got to be excited about the stars at least, but you said it wasn't like a super scientific minded or super academic minded family.
No, not at all. So I was pushed as a young kid, like, oh, you're super good at math, and there's a bunch of companies that are now becoming, I think, a little bit defunct out west of Salt Lake City. One of the big ones is like Thiokol. They build solid rocket motors. So they built all of like NASA's solid rocket motors in the 90s. And so everyone was like, oh my God, you're good at math. Go be a mechanical engineer. And I was like, okay. Like, I don't really have a lot of drive for my career as a child.
Right. Yeah.
So
yeah, when you're a kid, you're kind of like, oh, is that what you do when you like math? You do rockets.
Yeah.
And so that was what you were kind of imagining as your future.
Yeah. I enrolled at Utah State University, which I decided to go to because it was the one that was free based on my GPA and ACT score. I didn't apply anywhere else when I learned that it would be free to go there.
Why would I go anywhere else? I'll go to the free place.
Literally. So I enrolled in mechanical engineering there, and then they were like, you have to take all of these classes, and there was a bunch of chemistry, and I didn't want to take chemistry.
I see.
I've never taken a chemistry class, which is kind of like my two truths and a lie ringer. Ever, not even in high school. Not even in high school. I don't really understand how I was allowed to do that, but yeah. So I was like complaining to my physics teacher in high school, and she was like, "Just do physics," and I was like, "Can you do just physics as a major?" And she was like, "Oh, yeah." Then I just went to the physics department because they would let me take geology electives rather than chemistry. For the science.
Oh, okay. So they're like, if you take this major, you won't ever have to take a chemistry
Literally.
class.
Yeah. Bless that physics department. I don't know if they're still allowing people to do that.
I didn't take a chemistry class when I was in college either.
Yeah.
But I did take high school chemistry.
Yeah.
So I can't claim to be quite so non-chemistry
poorly
pure.
Studied.
So poorly studied as you. But I didn't take a chemistry class either.
Quantum mechanics is basically like all of that, right? I took a lot of quantum mechanics.
It's supposed to be, like in theory, if you know all of quantum mechanics, you should be able to do chemistry.
That's right.
I think in practice that's...
yeah, I think you're right.
Okay. So then... So that's kind of how you got on that track. You were like mathy, then sciencey, and then in college you were like, oh, physics. Okay, good. And then, so how then did you make how did you go from that to astrophysics?
I didn't realize that you could do astronomy as a job until very late.
It is kind of weird that you can, right?
Yeah. So I was like taking the physics classes, and my undergrad was like, oh, we are like so good at undergrad research. Students do research in their senior year, which now is like, I think not something that is seen as like, wow, we're so great at undergrad research.
Right.
But so they were pushing people who were doing like well in the program to start talking to faculty about doing research in your like junior year. And I was like, boy, this seems like pretty tight if I'm deciding to go to grad school.
Right. Yeah.
But yeah, so I lucked out. There was one professor who, spoiler alert, actually ended up being my PhD advisor. So he was at Utah State at the time. His name's Shane Larson.
Oh.
And I like wandered into his office and was like, I want to do observational astronomy. And he was like, what?
Okay.
Yeah.
But this person ended up being your PhD advisor.
Yeah.
Because what happened?
Windy pathways.
Windy pathways.
Super windy, lucky pathways. So, so he and I did some work that we had like a 20-inch telescope on top of the physics building. Mm-hmm. And he is an expert in like general relativity, gravitational waves, beyond GR theory type stuff.
Oh, okay.
And so I was like, but I want to do observations. And he was like, okay, like maybe we can measure the like post-Newtonian precession of Jupiter's moons, because theoretically you should be able to measure that the same way that you measure with Mercury.
Oh, sure, like you measure it with Mercury.
Yeah. And so we didn't really get...
Okay, but it was a fun idea for a thing.
Yeah.
That's a fun idea for a project.
Yeah, so like I did that, and then I applied to grad schools. I failed the physics GRE miserably. Like miserably, 7th percentile.
Did they tell you failed?
Well, I think when they give you a 7th percentile, it means that you failed.
Like, I guess I should probably. Okay. Yeah. Wow.
Really, not great, but also for whatever reason didn't stop me from applying to grad school. So I basically just applied to schools that didn't take the GRE.
Okay.
And I was like, okay, like I'll apply and see what happens. And there was a school, University of Georgia in Athens. So I got in, and I was like, all right, like looks like I'm moving to Georgia.
That's crazy.
It was completely wild looking back now, what I know.
Well, now you're going to be like the go-to example I'll use when people say, because this GRE exam, for those who don't know what we're talking about, is the exam that people will take when they're going to grad school. And in the past 3 or 4 years, a lot of universities have stopped requiring it, and some people disagree with that decision. But now you're the perfect example to me of like you can get a terrible score on the GRE but still be extremely successful scientist. So I guess it's not a very good exam.
I think it's not a unitary good thing, right? Like probably some people who do well on it might also do well, but there's probably other indicators in their applications. I
mean, it tests essentially like very textbook type problems, and it may not. That may not be that. May not need to be good at those to be a successful scientist.
Definitely. I remember very clearly thinking, I haven't taken quantum mechanics yet, and they are testing me on quantum mechanics.
You hadn't taken quantum mechanics?
I took it senior year.
Oh, I see.
And I was like, what the hell? I'm not going to do well on this exam that I spent $200 on.
Yeah, it's expensive too. I remember that.
Yeah. But anyway, that's, maybe a different podcast.
Maybe.
Just the physics GRE alone.
Just talking about the physics GRE alone. Yeah, that's true. But okay, so then where were we? So then you went to Georgia. What was it?
Yeah, Georgia. University of Georgia. And that, I literally went there because they would take me. There wasn't really any...
That's why I went to NYU.
Yeah. I mean, listen, like that's, I think, so...
NYU is a great school.
Yeah, great.
But
I think moving to New York is a little more fun than moving to Athens,
I was already living in New York at the time.
I see.
But so it wasn't as big of a wow. But yeah, it was, I had people ask me, why did you end up going to NYU? And I go, that's because they let me in. Yeah,
right. So I remember very much as a senior undergrad feeling like very backed into a corner. And I had inklings already that like, it just wasn't going to work out for me. A lot of the faculty there were kind of like working in things that I wasn't super excited about. One of the people I could have worked with, was a starting faculty and was like, dude, I'm full on students. I can't take any more students. Like it just, things like weren't working out too well. I did go though and take some really excellent grad courses, which was useful moving forward. But I basically emailed my undergrad advisor in a panic in like February the following year, just saying like, hey, all these people are saying like, there's no reason for me to not be able to join their research group except... And then something that didn't make a lot of sense. And so I was worried that I wasn't going to be able to do any astronomy research. And he was like, yeah, like, that doesn't really sound like this aligns with your goals. I'm moving to Northwestern. Do you want to move to Northwestern? And I was like, hell to the yes.
So That's pretty sweet.
It was a wild,
Wow.
yeah.
And then from then you that's pretty nice. And so then so how did he manage that? Did he just negotiate it, or basically say anyone he wanted to take with him?
It was not an easy process.
Right.
Yeah.
I would think.
I may or may not have been copied on some emails that I shouldn't have been copied on. I don't think everyone in the department was very excited about a grad student who failed the physics GRE, like rolling into Northwestern. But
well, I'm sure they're proud of you now.
Yeah. They've said as much. We've buried the hatchet.
Okay, good.
But he had a grant to pay a graduate student, and he basically said, I can bring this grant and bring the overhead to you guys, but it's attached to this student.
Oh.
And they were like, okay, whatever. Like,
Right.
if she comes and she fails out, it's not our problem.
Right.
Like, you're going to deal with that.
Yeah.
So I showed up, past like half of their qualifiers on like the thing coming in.
Yes.
And so I think that helped.
Oh, that helped give them the
quell
sense that,
the
okay,
fear.
she knows a little bit of what about this stuff.
Yeah. And then I just like was at Northwestern, and it was a total sea change. I think it helped that I just was like, as an undergrad, I didn't realize how interested I was in gravitational waves, and like how excited I was at the prospect of like, oh, like this is a new thing. Like it was like 2013, 2012, 2013. Like no one knew that gravitational waves was going to be this massive thing.
Yeah.
But the energy was high at Northwestern for that stuff. And so I was like, yeah, like this is what I want. I want to be in a high energy place where there's a bunch of people who are like peers and near peers and faculty who are all excited and invested and yeah.
That's very cool. So yeah, the enthusiasm is huge. And so then, so is that what you ended up studying when you were a grad student? What were you working on?
I was at one point, I think, the only grad student funded in the entire United States to work on LISA science, because LISA was canceled. Go ahead.
We should
explain what LISA is, because people don't necessarily know.
LISA is a gravitational wave observatory that does not exist yet. It still does not exist yet, but it's a complement to other methods we have for detecting gravitational waves, these ripples in space-time. And the thing that's different about it is that it would be launched into space, and it was a space-based gravitational wave observatory with depending on how well it's funded, with like 3 different
definitely 3 detectors.
Detectors, good.
Yeah.
Okay, yeah. At the time, though, it wasn't certain.
Yes.
3 different detectors that would bounce lasers back and forth between them to determine if the space between the lasers was being warped by a gravitational wave.
Yeah.
So anyway,
no, that's good.
But that was what you were like focused on at the time.
So Shane, my advisor, is a big LISA guy in the United States. And in 2013, LISA had been basically formally canceled by because NASA pulled out in 2011, I think.
But Europe stayed in.
Yeah, Europe stayed in, and a bunch of work was done by a group. I think they called it the GOAT. I don't know what that stands for. Gravitational something. Okay. But they did a test to say what happens if we reduce the number of laser arms from 6 to 2, and it was like, you'll cut the cost in half, but you'll lose 90% of the science. Right. And I helped do some of that work, but basically Shane had been like squirreling away this LISA money because he kind of saw the writing on the wall in 2011, like, we're going to need to continue the science so that we don't lose like brain power.
And it's interesting the timing of that, because this was still before we had detected a gravitational wave at LIGO.
Yeah.
And so so if you knew that was coming soon, then you'd be like, there's going to be a big enthusiasm for this, and it's going to, people are going to be back on board and wanting to do it.
Yeah. It wasn't like that. So that's my very first AAS was in 2011, and I'll never forget. Bless Shane, he included me in like astronomy community things at a very young age that I think most people were not necessarily involved in. So the first thing I went to at AAS was a NASA town hall. Okay. And the people who now are working on Roman, but I think it was W first back then, were basically saying, cancel Lisa, this is a sham.
It's it's never gonna.
We're never gonna see gravitational waves. Lisa Pathfinder hadn't launched.
Right.
We don't even know the rates of these things.
Right.
All these different things, and so the community opinion about gravitational waves was very low.
Yeah.
In 2011 through 2013, and then even still all the way up until the first detection.
Right.
In 2015. So.
Oh, I got that wrong. Last episode, I said it was 2014. I should really look these things up.
It's in the name, GW 150914.
Well, I didn't remember that was the name.
Yeah.
Anyway, I thought it was 2014.
No worries. Wrong. Well, 14. It's a September 14th, 2015. Or
maybe
September
that's
15th,
why I thought it was 2014.
Yeah.
That could be.
Yeah. So in any case, like, I joined Shane's group. He was like, we're going to work on these pairs of binaries called double white dwarf binaries. Mm-hmm. So they're like the end states of stars like our sun, which most stars will turn into white dwarfs. But they have companions. And this source of gravitational waves, which is just close double white dwarfs orbiting close together, is actually the largest source by number for Lisa, because predictions are that there are between 30 and 70 million double white dwarfs just in our galaxy.
Just in our galaxy alone.
Yeah.
Okay.
Well, because if you think of every star that formed over the entire history of the galaxy, we think between 15% and 50% of them have companions, and so they all turn into double white dwarfs. And then they don't really go away after that. They just kind of hang out forever. So
Right. And they'll just sit around and emitting gravitational waves.
Yeah, like emitting small amounts. They're in orbits from a few hours down to like a few minutes. Yeah. So that's what I was working on, predicting double white dwarfs.
Okay. All right. Yeah. And then I don't know where I am on my list of questions, but that's okay. Why don't I ask? Here's a question I have. When do you feel like you learned how to be a scientist?
Oh, that's a tough question. I think the first time that I really felt like I was like doing the thing, like for real, was actually after the LIGO detection. So I was kind of like I'm just doing this stuff. Lisa's at least 10 years away. Right. I just like living in Chicago. I'm a grad student. Like I'm doing my best.
Something.
Yeah. Like I'm doing my best. I'm paying attention. And then, so Vicky Calogera's group plays a huge role in the LIGO, not detection, but characterization.
To make a distinction, LIGO being the one that already exists, that's the ground-based observatory one in Hanford, Washington, one in Livingston, Louisiana. Yeah. That we're now very proud of, but because it did detect gravitational waves in 2015. But anyway, sorry, go ahead.
Yeah. So Vicky's group was doing a ton of work on the characterization of these signals, and so when they announced the first gravitational wave detections, we had a ton of conversations through different group meetings and things about these are the properties, where did it come from, how could it have formed, these kinds of ideas. And I remember sitting in a theory group thinking, the way that these things can form at the time was thought to be predominantly through either isolated binary evolution, where the binary stars interact with one another, and then eventually produce very short orbits that can produce black holes that merge within the age of the universe. And then the other dominant thought was that maybe they formed in these dense stellar clusters called globular clusters. And coincidentally, Northwestern also had a group who are world experts on globular clusters. And so I had been learning about isolated binary evolution and globular clusters for years now. And I was like, the clusters are all producing very eccentric binary black holes, and isolated binaries produce a little bit less eccentric binary black holes. And that's just because the physical processes that bring them together are very different.
Right.
And so I'm sitting in theory group, and everyone's talking about could we measure the spins of the black holes? Maybe the masses are different. And I was like, the smoking gun evidence is eccentricity to tell whether or not something is dynamically assembled. But ground-based detectors like LIGO will never measure eccentricity,
Right.
because by the time you're radiating gravitational waves at 1,000 hertz, like there's just nothing left. There's no eccentricity left in the orbit.
Maybe we should back up and explain what all that means. So if an orbit is eccentric, it's like our planets or our solar system are pretty close to circular, but there's some little bit of eccentricity. But meaning eccentricity meaning how non-circular your orbits are. And so if stars sort of form, a binary system sort of forms randomly, it might be very eccentric at first. And then if it becomes a binary black hole system, then that binary black hole system would be eccentric. But gravitational waves very strongly circularize these orbits. So by the time they actually merge, they'll all be circular. It's what our expectation is.
Exactly.
So, but you're saying you can still tell the difference between them.
We should be able to tell the difference when LISA flies. So when we launch LISA's at a lower gravitational wave frequency, and so the size of the orbit is larger. But also, if there was an eccentric orbit when the binary black hole formed, there will be residual eccentricity,
and they'll be able to measure that with LISA.
And LISA should be able to confidently measure the eccentricities even at pretty low values, and just more or less read off from the measurements
tell us where these binary black holes were formed.
Yeah.
So
that was my very first paper.
Like, I was like, dude, something that is relevant and people hadn't thought of.
Yeah. I mentioned it in theory group, and Fred Razio, who is the AppJ letters editor, said, you should write that up very quickly. and then I initiated this is like real. And so then that was kind of like a real kickstart to my research career, where I kind of dropped everything else that I was working on, and we put together that paper, and it's...
Wow, that's cool.
It was a fun, exciting paper.
Yeah. Well,
Sure.
It's always more fun when it feels like when you have that moment where you're like, oh, wait, this is a thing that I bet that maybe people haven't thought of. Yeah. And whereas like previously you're going through like, I guess I can compute this and that, and then it'll give us some answer that maybe someone will care about at some point.
Yeah, totally.
Which is a lot, and both of those have value to them, like even if you don't see the immediate payoff, but it is always more exciting when you have like, this is going to be a big deal.
Yeah.
So that's very cool.
Yeah.
Now you're an astrophysicist. What are some things you like the most about your job?
Oh, that's a fun question. So I just started my faculty job at Carnegie Mellon in September.
Yes.
And leading up to that, I was very fearful of starting a professor job because it just seems like there's so much to do and so many responsibilities.
Yes. Your job description completely changes.
Yeah, and I think it kind of felt like the final frontier of uncertainty, where I had been a postdoctoral fellow after my PhD for like 5 years, so I felt like I knew what I was doing with the science stuff.
Yes.
So I spent a lot of time thinking actually I didn't want to do faculty, and then I got the job and was like, oh no, like now I really have to do this. And what I've learned in the past few months is that my favorite thing in the entire world is helping students achieve whatever they want to do. And it doesn't have to be science. It can be like a small thing, like helping people with homework problems.
Right.
Or it can be like a super big thing, like I'm now helping or just finished sort of like chatting with some students deciding what grad schools to go to. Like that's, I derive all of my happiness out of that.
It's a really good attitude to think about the job in that way, as now your job is to like just help people. I mean, you can do there's other things you do, of course, but like now if you think of your primary responsibility is just to help other people, it becomes much more, I don't know how it feels like it's a much more human job, you know, as opposed to, well, okay, I'm going to calculate this thing, I'm going to solve this problem. Totally. Everything from mentoring your own grad students to teaching. And I love that stuff too.
Yeah.
It's and when you, I mean, obviously you're expected to keep doing everything, of course, which is the stressful part. But when you can sort of step back and just be like, right now, my job is to teach this class to these students, and it does. I don't know. You can, for me, that can have a very calming effect. Like right now, all I'm trying to do is teach these students how, like, gravitational waves work.
Totally agree.
and it's much, to me, that's more relaxing. Some people find that very stressful because then, like, I have to plan a course, and so that's, you know. But that's good. So, is there anything you don't like about your job?
Right now, I think the thing that I don't like about the job is writing grants and not getting grants.
Oh God, tell me about it.
That's the main thing. I think it's tough.
Constant rejection.
Yeah, and like knowing how much work, like collectively, our field is doing to prepare grants, facilitate grants, review grants, all for like 10% of people to get them just feels like.
And you would
I don't really get it.
You would hope you'd get used to the rejection after a while, but I haven't yet.
Yeah. No.
It's still like, but I put all this work into that proposal.
Yeah. That's the one thing.
Yeah. I don't like it. Would just a large portion of your job is just begging people for money and then have them tell you no.
Yeah. And then like having the money mean something.
And it matters, right? You're going to have to you need to pay your students to make sure that it matters to a lot of people, not just yourself. So that does suck. But I'm sure you will be very successful. You're just getting started.
Just starting.
So okay. Whatever. There's other questions, but those are boring. All right. So why don't we get into the actual science? Yeah. You've already started. You're way ahead of me, and I appreciate that. You were like, let's quit talking about me. Let's talk about binaries. So when you meet a new grad student or a fellow scientist and they ask you what you work on, what do you tell them?
I say binary stars and code. Binary stars and code. Yeah. That's mostly what I say.
Okay. So, and then let's elaborate on that.
Right. Yeah. So that's, it's funny. There's the place I did my postdoc at, the Flatiron Institute, we often get a lot of visitors, and so we have to do introductions with like 30 people, and so it's ingrained in me where they say, okay, what do you work on in 4 words or less? And so I would always say binary stars and code.
Can I say, like, that's one of my least favorite social things in the world is when a bunch, like 30 people are in a room and they say, let's all go around and introduce ourselves and say a sentence about what you work on. It's like nobody is listening to anybody else. They're all thinking about what they're going to say. Yeah. And it's totally pointless exercise that you spend like an hour trying to hear what everybody's...
I think that they kind of cracked the code a little bit by making it just 4 words, because then
that's okay.
Everyone kind of like makes jokes and you kind of remember. But
I guess so. I always said, I always would say, I'm Paul and I do hydro. That's how I would do that. But they would...
and then people would be like, what does that mean?
Yeah, they'd be like, ask me later. Like, if you're really curious, there's no point to me, like... trying to summarize my research to an entire room who is all just trying to think about how they're going to summarize their research. But anyway, good. Sorry, that was a little aside. It's my pet peeve is the going around the room introducing ourselves.
It's a fair pet peeve. It happens more often than it should.
Yeah. And also, some people don't want to introduce themselves. Yeah. Some people just want to sit back. They'll introduce themselves when they feel like it. Yeah. Anyway.
Good. So what I mean with binary stars and code is I am very interested in orbital dynamics just in general. I'm interested in what happens when 2 stars interact. Okay. To understand what happens, you have to first understand what the star would be doing on its own anyways, like burning its hydrogen into helium, doing the like standard single star evolution stuff, which is mostly just burning its hydrogen into helium.
Yes.
But then as they get into the later stages of their life, they start burning helium into heavier elements and all of that stuff. The radii of the stars change considerably. And so if they have a companion, it's very likely that they will either lose mass to the companion and have the companion gain a bunch of mass through that, or their orbit's going to change significantly, or you could even get like a merger between two stars.
Okay. And it's interesting. I know that's one thing in astrophysics that I like is a common thing that people who know a little bit about binaries but not much will say, like, we don't know anything about binary evolution, because single stars, we've put a lot of time into developing codes that can evolve a single star and understand like how it burns from hydrogen to helium and how it will spend its entire life and how it will expand, as you said, and grow in radius. But then as soon as you have another star in there, it just makes the problem way more complicated. But of course, a lot of your work has been actually solving that problem and figuring out how to... You weren't going to say that yourself, but... No.
Well, one thing that I'm trying to really convey to people more recently in my talks is that you can write down most of binary evolution with just equations. It's just analytic, and then you add tuning parameters. And so, for example, if a star is donating mass to a companion, based on the stage of that star, you know how fast the mass is lost. You can guess how much mass the companion can accrete based on its stage. And you can just calculate analytically, okay, based on how much mass is exchanged and how fast the stars are spinning, you just do it. You just calculate, okay, like the semi-major axis changes in this way due to these things. And it's not, like, it's actually not that, like, it's basically graduate classical mechanics.
Yes.
So... Yes, of course. It's not that mysterious, but people think it is.
Yeah. Well, that's right, because, I think, I would say... First of all, it's a little more... I mean, I'm sure it's like when you get into the details, there's all kinds of little things, but... But yeah, you're right that a lot of it is perception. So
like students will walk in and be like, "Oh my God, like you have this 5,000 line code," which I know for some people is like that's like a baby code, but it's like totally a baby code. But that's part of the reason that I like the code that I work with is that I can keep it all in my brain.
Yes.
I have friends in numerical relativity, and they're like, I can keep 20% of the code base in my brain at any one time.
Right.
Because it's so big.
Yeah.
But yeah, they walk in and they're like, I could never understand all of this, and I show them the papers.
So
it's like
code,
40 equations.
Just because I don't know the answer to this question, your code, you wrote it entirely every line yourself?
No.
Okay.
No, we hybridized a code that was written originally by Jared Hurley.
Okay.
So the code that we built off is a code called, it's like a combo of codes. SSE stands for single star evolution.
Okay.
And BSE stands for binary star evolution.
Okay. So you can have multiple modes that you run it in.
And that was about 3,000 lines of Fortran, which is, and it does algebraic fits, like polynomial fits to stellar evolution equations for single stars, and then does these binary star calculations that I was talking about.
I see.
And so that was released in 2002.
Okay.
And we updated a bunch of we actually still use the same evolution algorithm because it's fantastically means tested. That paper has like 1,600 citations.
So there was existing algorithms for how to evolve a single star, and a lot of what you've done is try to include all of the effects that come with having a binary.
They actually also did a lot of the binary effects.
Okay.
We just updated the algorithms with updates in our understanding of massive star evolution and mass transfer and different things like that.
Right.
Like a lot of things changed between 2002 and like 2015, and so we've just been working off of this public code and like adding new prescriptions, working with the algorithm, and then also just actually the vast majority of what I spent time doing was making it easy to use.
that's a big thing, because you're making a public tool.
Yeah.
And you want people to use it.
Exactly.
You want to actually have people get use out of it. I remembered. It reminds me of a story that I heard about Bill Paxton, who was the author of the Mesa Stellar Evolution Code, when he used to work for Xerox way back when, and they were first developing computer code. And he of course he argues with everybody, but he had this big argument with them that like they were calling it code, like it was proprietary. No one was allowed to know about our code. And he's like, no, it's a language. If no one speaks the language, it dies.
Yeah.
You need to like make it public, get it out there, or no one will use your language. And he was right. But yeah, that's exactly right. You want that, making it usable is a huge part of making it a living code that actually is a part of the community.
Yeah, and we kind of pride ourselves as being, a lot of these codes, because they're developed by like one person and kind of a bit proprietary, it's either that or some of the codes have started to actually hire software engineers.
Oh, really?
Yeah, which
I didn't know that.
Yeah, it's an interesting development, and I worry about it.
People listening are like, aren't you all software engineers? No, we have no training in how to do this. Yeah. We just kind of figure it out as we go.
Exactly.
And then,
so different codes now have different usability, I would say, and some of the other codes that are kind of like in the same space as mine, people have a really hard time downloading and using the code themselves because they have to compile it, or like it's in C++ and they don't understand the way
or it's in
Fortran. And so what we spend a lot of time doing with Cosmic, the code that I lead the development of, is it's completely accessible by Python. We made a bunch of features for building populations of stars, because the code that we built off of was just individual binaries.
Right.
And so we keep all of that in Fortran because it is lightning fast to run individual binaries. But then we've gone in and like added features that people are genuinely surprised that we can still do. So for example, you can, with Cosmic, and I don't know about this with any other codes, you can take a binary out of a big population that you find to be interesting and then say, oh, what happens if we change the different assumptions with a bunch, like change it a bunch of different ways. You can isolate that binary, re-simulate it, and then actually restart the evolution at different points in its full life.
So you can understand, I guess you're kind of doing experiments on this binary, you know, that you're saying like, okay, if I have a system like this, what if I change things? The kind of stuff you can't actually do in a real lab or something, right? I can't go look at a binary system and go like, hey, what if I change the mass a little bit? Would this change the system?
Yeah, what if I change just how much mass it lost at this given time? Or what if I change the direction of this supernova explosion?
How would that change its whole evolution?
Yeah, and you can do that now with like 3 lines of code, and for other people to do that, they have to rerun the entire simulation.
I see. Okay, so that's definitely usability.
Yeah, but that's the majority.
And with a very scientific mindset of this is the type of stuff you want to tinker with and experiment with, and so you want to make sure it's easy for people to do.
Right, exactly. Another one that we've done is like adaptive time steps for specific like outputs, where now when people are like, oh, I want to study this specific phase in detail, but I don't want those time steps for the entire evolution because the star evolves for billions of years.
So
I just want this 1,000-year
range of evolution.
Yeah. And that like was annoyingly non-trivial.
Oh, really?
To like get it to output.
That doesn't seem like
because you have to isolate a specific part.
You have to be able to identify it's in this phase now.
Exactly.
And then also update. Yeah, that makes sense.
And keep it still fast.
Right.
So yeah.
Okay.
So it's very like user-focused development rather than like we didn't actually change the science immensely by comparison.
But of course you always you say that, but I'm guessing over the time that you've done development, it's amounted to a decent.
Yeah.
But it's just not any given time. It doesn't feel like you're doing a major.
Yeah, there's like 1,500 of lines of Fortran that we've put in. That's like new binary physics.
Right.
All that stuff.
Yeah. So what is an average day, I guess, for you or your students? Maybe for you students nowadays, but like...
An average day for me is like 10 hours of Zoom meetings, I think.
Yeah, I'm sure a lot of people listening can
devastating.
Can identify with that sort of thing. But so for your student or for when you were a postdoc, I guess.
Yeah, the average day for me was I would start every day looking at the archive.
Okay.
For papers.
Mm-hmm.
I use a plugin that Danform and Mackie developed that it basically learns what things I click on and bubbles those to the top.
Oh, really?
Yeah, which is lovely.
Wow.
It's super easy. It's called Archivist.
Wow, I didn't know about that.
Yeah.
That's going to be the most useful scientific tool he's ever developed.
I know, right? Who knows?
I'm very much joking about that, but in case he ever listens to my podcast. Right. But anyway, that sounds very useful. I didn't realize he did that. But anyway, okay, so you check and see what's new, what papers are coming out that are new.
Yeah, and I mostly read titles unless I'm like, whatever, right. Like this is exciting, or my friend had a paper. If there's a paper that I'm really excited about, I'll usually jump in and read the abstract and then the conclusions.
Yeah.
And if it's somebody who I know, or I think it's like I knew a result was coming, one thing that I try to do, and I'm trying to get other people to do, is I actually send those people an email that's just like, congratulations.
Oh, yeah.
This is really cool that you got this paper out, because sometimes when you put papers out,
you just get radio silence.
Well, you get radio silence, or
you
people
only get
asking.
Negative, hey, why didn't you cite me in this thing? Yeah, that's true.
And so I like to add little positive things to people's inboxes.
I think that's great. That's a great thing you're doing, because I also think I do this when I probably shouldn't give myself away, but when I'm a referee, I make sure and always say several positive things.
Yes.
Because almost every referee report is negative,
Mm-hmm.
and for me it's extremely demoralizing. I just don't want to.
Yeah, my least favorite work day is the day after a paper has gone out on archive, because I get 20 emails saying you didn't cite this.
That's a lot more than me.
I think it's partially the gravitational wave field, but because it's a very everyone's I don't know, jockeying for citations basically. But yeah, so that's what I sometimes, depending on how long that takes, sometimes that's up to the first hour if it's a specific thing. So I sent one of those emails today. Okay. Which is why it's at the top of my brain. Then depending on what day it is, there will be something like a journal club or a seminar at my institution. So I always try to go to those. And then when it gets to actually doing research things, the thing that I like to spend the majority of my time doing now is actually more code development.
Okay.
And I think that's probably a function of I'm working with a lot of students who are more junior. And so we're in a stage where they're basically deciding whether or not they want to work with me for their entire thesis. And so they're working on smaller projects.
So you're not going to have them in the code making modifications or stuff like that, but they might want to use the code for some problem. Yeah,
and so I have these ideas for what I think would be really exciting, and then I realize, I didn't fix that part of the code yet. And so I'm kind of laying down railroad tracks ahead of the students that are doing the science a bit.
That's right. So do you end up so when you were a postdoc, did you end up doing as much code development, or is this now you're kind of shifting gears and now I guess now I have time, that's when I can focus on a little more?
Yeah, I did. I think I started making that shift a little bit more because I had a magic situation where I had an extra year of my postdoc, but I applied to faculty jobs early. And so I spent a lot of that. I deferred for my faculty job for a year, and I spent that last year thinking a lot about development rather than science.
Okay.
And I think I'm kind of still in that, but now there are grad students to do the science part. Yeah.
That's good. Okay. So reading papers, going to talks and coding.
I think that's mostly sometimes it's like, oh, actually, that's a complete lie. It's not mostly it. Also, giving comments on papers takes so much time.
Yeah,
like
that's true.
People who are collaborators or other students that I'm working with at other universities.
It only takes a long time if you want to do a good job.
That's right.
So
yeah. That's I have like one curmudgeon rule, and that is if somebody doesn't give me comments on a paper, I will not add them as an author.
Oh, if they just no feedback.
Yeah, if there's no feedback and it's clear that they didn't read the paper, then I don't really know what they contributed. And so I'll say that from the get-go usually with people, and I get comments.
That's fair.
Yeah.
That's pretty good. It's funny how things like that, like they probably would have, but like they just didn't get around to it or something. But like you just need that prodding, and they go, oh sure, and then
totally. Yeah, like that's I think it also significantly improves the papers.
Yeah,
if you actually get comments from lots of people.
Absolutely. The papers that I get that people think that people find the craziest are the ones that I write just by myself.
Right.
And
yeah, that's
because they're it's just one voice, without any like modulation of that, and it does come off a lot more kind of nutty.
Totally.
And so
but that's can't. Yeah, I don't know. Science is a community endeavor.
That's right.
For sure.
That's right. So. And so yeah, exactly. Then if you get more people, then they can be like, oh, people. If you say that, people will think this. Maybe if you point this out, then it'll make it clear, and then the paper just gets more rich and makes more sense. It's not just one person's ramblings. So yeah, I agree. I still write papers on my own sometimes, and I regret it usually. So
yeah, I've never done a single author thing. Yeah.
Okay, so what do you think would be your most, or either your most impactful contribution, or something you were most proud of, or think is most interesting, or something you think is exciting right now that you're working on?
I have different answers to all of those questions.
Which one jumps out at you?
My favorite thing where I actually feel like I did something is when I'm looking at the archive, I see that there's a paper that cites our code paper, and I haven't heard from those people at all.
Yes.
And they just picked up the code and did something with it.
Yeah.
And like they did awesome work that I was never going to be able to produce, but because I did the work to develop the code, it's like taken on its own identity. It's like my favorite thing.
I like it when that happens to me too. It doesn't happen to me very often because my code is not, I don't make efforts to make my code user friendly. I put it out there at public, but I don't like, so even actually it's more special when it happens to me. Somebody just downloaded my code without even telling me and just like did some science. That's crazy.
It's so cool. I love that. That's like my favorite thing. Yeah.
But so what would be I guess I was looking for something about a particular science result that you found.
Yeah, so that's a little different. Right now, the thing that I'm so excited about that is more or less coming to fruition now over the past year is at the end of my PhD in 2017, we had a colloquium from someone who came and talked about the Gaia Space Telescope. And prior to that, my entire work was all focused on gravitational waves. And I was feeling like a little stressed because it's a really competitive field. Like I said, you get emails and whatever.
Right.
And I was like, there's got to be other ways to like constrain binary evolution. And this guy came through with Gaia, and I was talking with a postdoc, Saurav Chatterjee, who's now faculty at the Tata Institute for Fundamental Research in Mumbai. And he was like, I bet you we could predict what Gaia will see for black hole binaries, but in this case, it's a star that's still going throughout its life that has a black hole companion. And so we did this paper where we predicted what are the features in the population of black holes that have stellar companions that Gaia could observe.
Okay.
And we've now hit the past in the past year, there are 3 that have already been announced from the Gaia collaboration.
So, okay, let me back up a little bit. So Gaia
Yes.
Gaia is a, well, do you want to explain what Gaia is? You'll do a better job.
Totally. So Gaia is a telescope that I will throw down for as probably the best dollar for dollar investment that's ever been made. It measures the positions and velocities of every star that's bright enough to be observable by the telescope. And what that means is it has told us the position and motion of over 1 billion stars in the galaxy.
Okay, and these are basically our neighborhood, in the Milky Way.
Out to, it basically covers our half of the galaxy.
Our half of the Milky Way. Wow.
So we can't see through the galactic center,
right?
But we can see out into the outer edges, like in the halo, and in towards the...
Okay, and so then you have this big data set of all of these stars, where they are, and what their current velocity is.
Yeah.
And so now what do you do with all that information? Obviously, it's a lot of data. So then the answer, I guess, is many things. But
so many things. So it's, the amount of science coming out of the Gaia telescope is like, I think we're going to continue to see results for decades, basically. One of the flagship things that the Gaia telescope was designed for is to basically understand the assembly history of the Milky Way, because all of the stars that are born together, they have... So one thing that Gaia also does is it takes a spectrum, so we know what the chemical properties of all the stars are too.
Okay.
And so that helps us disentangle. Basically, people have learned like what the last major merger was with the Milky Way. We know where those stars are, what their properties are, where they're going.
So the last major merger, meaning the Milky Way, previously there would have been 2 galaxies that merged. We don't really know much about when, but apparently now we know when that happened last, when 2 galaxies merged to form the Milky Way.
And like there's clusters that people are finding that have fallen in and gotten mixed with the population. There's all this stuff that you can do just by so we know tracing the orbits.
If you know where everything is now and where it's fast it's moving, you can basically, I guess, trace back where some things came from and how, okay.
Exactly. The other thing that you can do, which is, so that's kind of like bulk motion in the galaxy.
Right.
Like these are like huge moving groups where there's like 1,000 stars that are all basically on the same trajectory.
Right.
There's a modulation to that, which is if there's binary motion. And so if a star is orbiting a companion of any kind, you'll also just see it literally moving on the sky.
Right, because it's moving because it's in orbit, so it's in a circular motion. If they're close enough, you'll see that circular binary motion. Yeah. In addition to their bulk motion through the galaxy.
Exactly, and so it's a way to just find literally millions of binary stars.
So now, I guess the point is now we have a huge population of binaries in our galaxy. And so so then what does that mean? What can we learn from that?
Yeah, so, oh my God, we don't even know all the things that we can learn from just that population. So what we've been doing and what others have been doing in like the very first studies out of this binary data set is if a star is orbiting something that is more massive than your average star, the physical size of the orbit will be much larger relative to how fast the orbital period is.
Okay.
Because the more massive thing is making the less massive thing fly around faster.
Okay.
Like basically. And so one of the first figures that we made with this data set was literally tell us the projected size of the orbit on the sky versus how fast it's orbiting. And there were like 15 sources that popped out above the standard population, and there were 2 black hole star like companions in there.
I see.
And the other ones were kind of like weird data, like there were like spurious measurements or like...
So there's ways of going through this data and finding like you said very earlier, finding systems where one of them is actually a black hole.
Yeah. or at least massive, and then you zero in and say, okay, is this just a big star? Like, is it something else?
You can always follow up and look at the system with a different telescope and say, look at it more closely and say, is there actually a star there, or is there? So the idea then is this is like, you don't see the black hole, but you see the star, its companion, and it's moving in a way that's like, well, it's got to be in a binary system.
Yeah, exactly. And the only thing that could have that mass is a black hole.
Right.
At that, like,
when it's okay.
Yeah.
Wow.
So we found them, and I predicted these things in 2017, and kind of ran around for years saying this is going to be a total game changer. You just wait, and we've started to pull them out of the data. And
what I love is
so exciting.
I feel like it could be an unappreciated thing. It's like, this is a new way of finding black holes. So, we have, gravitational waves, we have, what other things?
X-rays.
X-ray binaries. We can look at a few of them directly with EHT, but like, this is one where this is a totally different thing. It's, you find a black hole by looking for something that has a companion that's invisible, basically, and then making constraints on what it could possibly be.
Totally. And because Gaia tells us literally exactly the motion of the star, we get precise measurements. So the black hole masses are measured. The one is like 9.8 plus or minus 0.1 solar masses. So they're way better mass measurements than gravitational wave measurements. Yeah.
Well, that's very cool.
And then because it's got a stellar companion, you can assume that they were, even if it was like dynamically assembled in some way, what the chemical composition was of the progenitor star of the black hole. And its age because what the stellar companion age is. Like, so you get all of these clues to the progenitors of the black holes.
Oh, okay. So it also, right. That's not just showing you, okay, there's two black holes that merge, like LIGO can tell you, but it's actually not, it's telling you something. It's at a certain stage of evolution where you're learning how black holes form in the first place.
Yeah.
Okay. How many of these have we found?
So there were 2 found in globular clusters, actually, back in 2018. And then the Gaia black holes, there were 2 that I was on papers with Karim Al-Badri that we announced back in 2023, right after the 3rd data release. And actually, literally like a week ago, Gaia BH3, the 3rd one.
A week ago?
Yeah, announced by the Gaia collaboration. Oh. And it's a whopper. So the first 2 black holes are really quite similar to what the X-ray binary black holes are. They're about 10 solar masses. They have 1 solar mass companions. The 3rd black hole is 33 solar masses.
Ooh.
I know, weird, huge, and has a really low metallicity, like 0.8 solar mass companion.
33 times the mass of the sun, and then what did you say about the companion?
The companion is 0.8. It's tiny.
It's just.
It's weird. It's so, it's really cool.
So then, do we have any expectation that should be in any way normal, or?
So if you go back to my 2017 paper, it exists in our predictions, basically.
Okay.
And the reason that it sticks around like that is because you basically just have to form, the weird thing about this is to have the weird companion mass ratio. So you have to start with a really massive star, probably 40 to 60 solar masses, and then have a really low mass companion.
Yes.
But otherwise, every other aspect of that the evolution points to these things are actually more common, because once you make a black hole, as long as like the binary survives the formation of the black hole, then the detection probability all hinges on the companion. And so low mass companions live for way longer than high mass companions.
Right. The longer, the bigger they are, the faster they burn through all their fuel. So then, I guess then you would expect, as long as these things are somewhat normal to find, that the one you would find a lot of these with a small companion.
Yeah, with low mass companions and also low metallicity companions, just because those are the oldest stars. Okay. And so there's been a lot of time for the black hole to, for basically all of any star that has formed in the age of the galaxy, can be added to this low metallicity, low companion data set versus like if it's a solar metallicity star, like a high metallicity one. Then
but it's still kind of crazy. I mean, it's not what I was imagining you would find, but I guess that's why we don't just ask what I'm imagining. We go and look.
It's funny because then back when I was presenting those results, I was thinking like, these are a little... like, I don't know if we're actually going to see these. And so people would say, do you actually really think that we're going to have, there's this figure of high mass companions that form from constant star formation and then lower mass companions that form from very old star formation. And everyone would always say, there's like, really, do you think that we're going to see these like low metallicity companions to black holes? And Kareem was like, you really got to start leaning on those predictions because like they're in there, like it's in that paper. So
wow, that's cool. That's great. Okay. So I know you're looking at your watch now. That's okay.
It's been so lovely.
I that's the thing is I have fun and then like I just get like, oh, let's talk about this now, and then it's time to wrap up. But that's okay. So I'll have one last question for you, which is, in your opinion, why should we care about astrophysics?
Oh, I don't like this question.
Okay, I don't know. We can cut it if you want.
I think, no, we don't have to cut it. I think that astrophysics lies primarily as a way to ignite excitement for science in our community. And I think it is an excellent tool by which we can teach students very useful critical work skills. But I don't personally believe that there is a morality to astronomy in any way.
This is something that we need to study.
Yeah. If somebody said, you can either fund astronomy or you can fund healthcare, I would say fund healthcare. I think every time.
But, of course, that's never the
it's not actually what's happening.
Right.
That's right.
It is possible to fund both, so let's not make it
sorry for just
don't defund our entire field.
I know.
But it's certainly possible to fund more than one thing. But yes, I agree. It what we do doesn't directly directly like help people in the same way that healthcare does, or even other branches of science do.
Yeah.
But yeah, it does. It certainly. Ashley Villar had a similar answer. So she
amazing.
Said, she said. But yeah, basically that it's a science that gets people excited and gets people interested, and if those people end up going on to be engineers or doctors, then that's great.
And also just like a conduit to critical thinking. A lot of undergrads come into college thinking, oh yeah, like sure, I'll take an astronomy class, and then you can, in a general astronomy class, you can teach a lot about critical thinking skills and quantitative reasoning and stuff like that. And so I think that's something that I'm really looking forward to.
That makes a lot of sense. And it's a good way to look at, like, if anytime you have a vehicle to do that, like it's motivating, rather than having a problem where you have a cannonball and seeing where it lands or something. Yeah. Maybe people don't care so much about that. Maybe some people do, I don't know. But but yeah, when instead you say, like, I don't know, how long does a star live, or I don't know, something like that, and trying to answer those types of questions may get someone excited to learn critical thinking skills. All right, great. I accept your answer. So then, all right. So I'll just wrap it up then. You have many many people to talk to, but so thank you very much to Dr. Breivik for joining us. I had a lot of fun talking science with you, and I hope you will join us again sometime.
Cool. Thanks.
One of the things I find most incredible when talking to all these scientists is how often they had a period where they struggled with getting to where they are in academia, and how easy it is to feel like they don't belong, and yet now they're a world expert in their field. Hopefully that inspires you to not get discouraged in your own pursuits and realize that any pursuit that's truly challenging is going to involve a lot of frustration in the early years, so stick with it. And thank you, Dr. Breivik, for that awesome conversation. And thank you to our listeners. We will see you next time. The Astrophysics Podcast is supported in part by the National Science Foundation under grant number AAG 2206299. The music playing right now and throughout the Astrophysics podcast was written and recorded by Britton Ashford. You'll find this music on her album Trotter. All songs are used with permission from the artist and producer. Please check out her music if you enjoyed it. This podcast is produced in beautiful Lafayette, Indiana by me, Paul Duffel, Professor of Physics and Astronomy at Purdue University.